All right, guys. So we're getting, I don't know if you realize this, but you guys realize that we're almost to the final. Tomorrow's frickin' December. What the shit? We're almost into 2024. Okay, sorry, with all obvious things, but what's in our near future? A week from today, does anyone know what's going on? Yes, good. We're reviewing for the final because a week from today is the review for the final because the following Tuesday is the final. I could have put the final on that Thursday. I made the decision for all of us to do it that Tuesday instead. Is that okay? All right. Okay. So I'm going to give you guys a practice final exam on Tuesday. I'll give you, or probably if I think about it, if somebody emails me, I can put it up on Canvas early, right? If you remind me, I can do that, and I can bring hard copies on Tuesday. I'll have the answer key for it on Thursday. I'm not going to try to shove another quiz in. Is that okay? Okay. To be honest, you guys should be upset. You want more grades, but you know, little average. Also, here's a couple of things how the near future is going to work. Section 9.1 is really silly. Have we talked about fractions? Okay, good. All right. Some of you guys look at me blankly, but I think that just means, well, yeah, dude, you were there. Section 9.1. In fact, the silliest thing about this book, but I kind of understand it probably mimics some of what you do when you're teaching young children, but I would think there'd be a little more overlap. The first part of the book assumes negative numbers don't exist. I've pointed this out a few times, yes? So we already did fractions. We just pretended like it couldn't have a negative number in it. Section 9.1 redoes everything, except now it allows them to be negative. So I'm not going to do it. We're not going to do section 9.1.
Do we not need to do homework for 9.1?
That's what I'm saying. That would be so evil. I'm not going to talk about it. You guys still do it. I'm not that evil yet. It's kind of funny because I remember 10 years ago saying, give me 10 more years, we'll see if I'm that evil. I'm not that evil yet, apparently. And then section 9.2 just adds in, what's the only kind of number we will not have discussed yet? Irrational numbers. Well, can somebody give me an example of an irrational number? A number that thinks the earth is flat. No. No numbers there. Irrational. Anybody know what an irrational number? Okay, what's a rational number? What's the root word of rational? Ratio. So what's a rational number? What's a number that is a ratio?
2.
I'll accept it because that's 2 over 1. So a number that is a ratio, isn't that a fraction? You with me? So obviously 3 over 4, 3/4, is a rational number because it's a ratio. You with me? 2 is also rational because 2 over 1. We just don't write the over 1 because we want to save time. You guys all with me? Therefore, how about 0.3 repeating forever? Is that rational? Who remembers? You guys know. You guys know this. What's the definition of a rational number? Anything that can be written as a ratio of whole numbers, right? Anybody remember 0.3 repeating? What is that? 1/3. So 0.3 repeating forever, rational, because it can be written as a ratio of 2 whole numbers, where the bottom's not 0. In fact, now I'm going to extend it to integers. We're about to get into finally admitting that negative numbers exist. So that's the integers, right? Is everybody with me at the moment? So all section 9.2 does, now that you understand, rational numbers are any number that could be written as a ratio. What's an irrational number?
That can't be written.
Holy shit. Now give me an example of one. So we remember the process we used when we had 0.272727? Didn't we do some finagling to make it become a fraction? Do you guys remember that? And it's in the book too, right? So I like the honesty. Somebody's like, I do not. know what the shit you're talking about right now, Jeff. We multiplied by 10 or 100, and then we subtracted. You guys don't remember that? So for example, does anyone know what 0.4545 repeating, what that is as a fraction? Does anyone know? Okay, so what do I call it if I don't know what it is? X, that's right, kids. Why does that number suck? Give me a decimal that I can make a fraction easy. 0.8. Why is that easy to make a fraction? Because it stops. And I don't care how long the damn decimal is. If it stops, I just put the 1, 0, 0, 0, as many places as it has. Does that ever stop? Damn it. So what I want to do is I want to kill, oh, this sounds so cool. I want to go kill infinity, basically. I want to cancel out the infinite part of it. So real quick, you guys, does this look familiar at all? We did this. What happens if I multiply by 100? Moves over twice, right? Yes? So now it's 45.4545 forever, yes? If I subtract 100x minus x, that's 99x. If I subtract this minus this, these cancel. Therefore, x is 45 over 99, which reduces to 5/11ths. Any decimal that is repeating or terminating can be written as a fraction. So any repeating, terminating decimal is rational, because rational is any number I can write as a fraction. So let me try again. Can you give me an example of a number that is irrational? Beautiful. Pi is irrational, as far as we know. 3.14159, I think it's 96, I can't remember. 3.1415, that part I know for sure. Real quick story. March 14th is Pi Day. You guys know that? March 14th, 2015, I was at a math conference, and they lost their minds. They had little pies, which is great. I love pies. So we had little pies, and oh, it's Pi Day. Oh my God. And we called it Super Pi Day. Because we're doing okay. Let me do this before. So it goes forever. As far as you can tell, there's no pattern to it. So as far as we know, it's irrational. So it is a non-terminating, non-repeating decimal. That's irrational. Anybody else know another? Doesn't have to be something with a funky ass Greek letter or something.
Is 0 irrational?
0 is totally rational. Yeah. Yeah. How about square root of 2? That's irrational. 1.414, blah, blah, blah. Okay. All right. So that's all section 9.2 does, is it says, hey, there's these other numbers that don't fit into anything. We're going to call them irrational. Okay. So when I would give my little talk when I was teaching pre-algebra, I would say counting numbers, 1, 2, 3. So I got one, I'm a caveman, I got 2 rocks, right? That's very insensitive toward cave people culture. Then I'm walking around and I lose my rocks. So I have to invent the idea of 0, correct? That's whole numbers. Then I have to borrow somebody's rock, because I need a freaking rock, I need a house rock. So I have to borrow a rock, don't I owe, am I not in debt now? So that's negative numbers. So that's where we are right now. Then I drop my rock, and it breaks in half. Fractions, right? Rational numbers. Then there's a weird guy on the rock sitting over there talking about square root of 2 and shit. And that's irrational. All right, anyway. So all that is me trying to say, chapter 9 homework is extra credit. You guys can do it, not. If you have time, section 9.1 homework should be very easy, because it's just a rehash of all the fraction stuff. Well, I'll say very easy, unless fractions still haunt your dreams. And yes?
Will we be tested on chapter 9?
I would only put bonus questions related to it, yeah. Now, listen, I could certainly give you, well, and we've done this. We have fractions and we subtract. Chapter 9, section 9.1 just says, oh yeah, a fraction can be negative. That's all it does. Do you understand? Yeah. So I'm not even gonna talk about it. We already talked about it. So technically, I'm gonna give you a problem from 9.1, and you're not gonna care, because it's the same problems we've done before. And 9.2, like I said, just introduces irrational numbers. Okay, so what we're gonna talk about today is we're gonna talk about integers. So integers are just adding the idea of negative. So for example, a lot of my college days, you could not describe it financially correctly if you didn't have the idea of negative, right? Unfortunately for young Jeff, right? I lived a very plastic life, let's just say. So what we're gonna do, let me ask you this. I kind of missed the fact, I loved teaching Math 88. That was where I taught things like 2 minus 7. I didn't love the fact that there were adults who needed help with that, but I accepted that was true. Everybody has different lived experiences. They had different things that got them out of school. I understand all that shit. So one reason I love to teach that is I don't get to teach that very often in college. So when I get to teach that, I get to like experiment, because for me, of course 2 minus 7, what's 2 minus 7? Negative 5. Of course it's negative 5. And then you got to think, okay, how the hell do I explain that to someone who has no idea what it is? You know what I mean? So that's exciting to me, right? Does anyone have any like real life example that could help explain 2 minus 7? Yeah.
I have $2 in my bank account, and I spent $7, and now I'm at the negative.
Yeah, now you got overdraft. And I love it when you're overdraft, you got less than no money, so they're like, we're gonna take more money away from you that you don't have. All right, that's a good one. Money is always good. Money is always good because everybody's gotta deal with money to some extent, right? Any other example? Money is perfect because most people have to deal with money. If you're teaching somebody who's like 8, have they had a lot of experience with money? No, so that might not be a go-to for them, but older, for sure. Anybody else have a different possible way to explain 2 minus 7?
Like a number line.
Number line.
Visual.
Sweet, all right, I like it. So we have kind of like conceptual idea, money. I have $2. I have to give you 7s, that means I gotta use a credit card. I'm in debt for $5, right? So I have $2. I owe $7. If I pay that off, I'll be in debt $5, which translates to negative $5. That's how we define debt, is with the negative. Or one way to describe that is negative numbers. Then we have the number line. Take a minute, figure out how to show that on a number line. Don't say anything. Just figure out how would you show. We've already done this, to be honest, right? Actually, let me make this a little bit different. And some of you guys should totally understand this is the same thing. So 2 plus negative 7, that idea. So I always think of, if I'm adding a negative, that is like adding debt. Okay. So on a number line, it actually is exactly what we're used to. Let me put 0 in here. Let me put 2 in here. You can do it, Jeff. So if I go back 7, so if I take 2 and then I add in negative 7, so negative is just going back on the number line. Where should I end up? Well, let's be more specific, Jeff. 1, 2, 3, 4, 5, 6, 7. So of course I end up at 1, 2, 3, 4, 5, negative 5. Amazing. Cool, I like it. So that would be, does anyone remember the name of that model? Measurement model, kick ass. Anything else? Anybody ever seen, okay, here's a really good movie, if you haven't seen this. Has anyone ever seen the movie Stand and Deliver? What's the name? His name? I think it's the name of the actor, I'm remembering, not the name of the teacher. But who saw it? Who saw it? Somebody saw it. You guys have seen it? Okay, if you haven't seen it yet, it's amazing. It's a high school teacher taking his class from like pre-algebra all the way through calculus. And it's just about his approaches and what he has to deal with the students and all that stuff. Really good. I know you guys are hoping to teach much younger people, but still, it's a teacher trying to deal with how to explain stuff to their students. In one scene, I love the scene. They're doing -1 + 1. And I really like this conceptual idea. Negative is digging, right? Going down. Positive is climbing. So if I do -1, I've dug a 1 foot hole. +1 is, you can think of it as putting sand in there, right? So if I have -1 + 1, there's a scene where the whole class, he's trying to get somebody to tell him what the answer is, and the whole class is saying, fill in the hole, fill in the hole. So what is -1 + 1? 0, it's crazy. So when I get a deeper hole, I think of it as climbing. So like if I have -7 + 5, so I have a 7 foot hole and I climb 5 feet, am I out of the hole yet? Do you see how that makes good immediate sense? Negative just means you're in a hole. Positive would mean you're out of a hole, right? Like I imagine like a ladder, right? So -7 + 5, how short am I from getting out of the hole? 2. So I'm still 2 feet in the hole. -2, because negative means I'm still in the freaking hole. You guys kind of with me? So it's taking the math out of the way for a minute, which I will agree is not the right place to start with people. Math captures ideas and makes it very abstract. This is making it immediate and physical. What about -7 + 9? What would that mean in my example? I'm in a 7 foot hole and I climb 9 feet. Now again, imagine the ladder. That's how I'm climbing. How much do I climb above the hole? So I'm +2. I'm 2 foot above the hole now. I'm out. I like it. Okay, cool. All right. Anything else? I think that pretty much captures most of it. Money's a really, really, really good one. I like the idea of negative being digging and positive being climbing out of a hole, right? We're going to get to this in a minute, but let me ask you this. What is -5 - 7? Yeah, so if you think about the whole thing, I dig 5 feet down, and then I dig 7 more feet down, so now I'm 12 foot in a hole. Why do you think a student would believe that's 12? I'm getting a little bit ahead of myself, but I don't care. We're talking about all this negative stuff.
Because the multiplication, the negatives cancel.
2 negatives make a, if you're not careful, I try not to say what I just said, but I know you guys have heard that expression. If I just say that, isn't that 2 negatives? And then I just say 2 negatives make a positive? What's up? Did you teach? What the shit? So what should I say? I think you just said it. When I multiply 2 negatives, that makes it positive. The thing I like to say about this is, if I have 2 debts, going back to money, if I owe you $5 and I owe you $7, the debt doesn't magically cancel. I've tried it. The bank said no. Right? So that I owe even more money now. Okay. What do you guys think we're going to use for manipulatives for this? So we've seen some manipulatives. We saw the fraction stuff. We saw the base. I think we played with base 4 or 3. I can't remember what we played with. What do you think we can use for manipulatives for doing a problem like 2 plus -7? This might be too broad of a question. So what we're going to do, I don't know if anybody knows these I brought. So this would be positive. They're supposed to be black, but oh well, I got blue. And these would be negative. So if I wanted to do, for example, let's do a few things. I'm going to give you some of these to try some stuff out. So how would I do 2 minus 7 then? What would I do? What does this represent? 2, right? Okay, let me get something to put behind this. Yes. All right, that's 2. All right, how would I represent negative 7?
7 of the red.
7 of these red ones. Now, what's really cool, you can do it now. There you go, buddy. What do you think? So now this is 2, negative 7. So this is, if I drew circles around this, what model would this be?
7.
Set model. Kick ass. So what happens when I do this? What idea do we need to develop? What's supposed to happen here?
So since you have 2 positive, you take 2 positive away, and you also need to take 2 negative.
Yeah, these two kill each other, right? And of course, what do I get? The red is negative, so I get negative 5. It's really, again, we want to come up with a way to capture the concept with little toys, little things that can actually hold and move. So this is really freaking cool. We're gonna do a lot of weird shit with this. So let me give you guys some of this stuff, and then I wanna develop, well, I need some for myself. That should be plenty. That should be plenty. What's the quickest way to do this? I don't know. You take it, take some and pass it on, and I'm gonna put this on the other side of the room. Take like 7 or so, should be enough for everybody. We shall see. Yeah, this should be better. Yeah. All right, cool. I was wondering where they would cross. Cross the streams. Gotta get there. Oh yeah, we'll do that first. Yeah. So, I think everybody good. Okay, yeah, just leave it at that. Thank you. So what we want to do real quick is we want to figure out what that is. That's key. That basically captures what you said about if I have 2 blue and if I have 1 blue and 1 red, they annihilate each other. They become 0. So of course we know what this is. Negative A plus A. How can I? And of course, what is that? Holy shit! What in terms of addition? How is 0 important? It's actually a key number. What's the name for 0 in relation to addition? The additive identity. Because it's what you add to keep it the same, correct? What was the multiplicative identity? 1. What was the multiplicative inverse of A? 1 over A. So it's the thing, the inverse is always the thing that I apply the operation the width to make the thing become the identity. So for multiplication, the identity is 1. If I give you a number like 4, what do I multiply to make it become the identity? 1/4. Addition, if I give you 4, what do I add to make it become the identity? -4. I like it. So if you just say, if I just said to you, what is the opposite of 6? You do not know what the answer is. Because how many ideas of opposite are there? There's one for addition, and there's one for multiplication, correct? So the opposite of 6 could be -6. The opposite of 6 could be 1/6. Okay. So if I want to kind of prove this, one way I could do it is, if I assume that A is positive, A would be here, so I go up A, and then I go down A. So of course I'd end back up at 0. Not the most stringent proof, but hey, it actually works. So if I want to do 5 plus -3, so what am I going to lay out here? Do this with me. What do we got?
5 blue
5 blue,
and 3 red.
and then I'm going to add to it 3 red. And now we officially understand that this is like 1 plus -1, 1 plus -1, 1 plus -1. They annihilate, and the answer is, unbelievably enough, 2. Now, real quick, something we haven't established yet, but we can sort of establish now is, what is this equivalent to? 5 plus -3, what's a better way to write that? A more efficient way to write that? 5 minus 3, right? Now, again, little people, they don't come into the world knowing this shit. That's something that we have to explain why that's true. This would be sort of a first step as to showing why it seems these two are the same thing. Because 5 minus 3 is 2, and 5 plus -3 is 2. Okay. Oh, Haley, sure. You gotta grab some chips. So grab a handful of those, handful of those. Coolness. You're ready. Alright, so how about this problem? -2 plus -4. Let's go ahead and lay that out. Yeah, open that, I'll fill in the details. Yeah. So of course, this one's not too bad, right? What do we get?
-6.
Yeah, we get 2 of these, and then 4 of these, so then -6. Incredible. Now, I'm gonna kind of bring back to this, because there's a really nifty, short way to remember what to do with the signs that we're going to come back to. So this was incredibly enough 2. This was unbelievably -6. All right, so what about this? What about -5 minus -2? Lay that out. Figure that shit out. Don't change anything about the problem. Do it exactly as it's put down. So of course I'm going to lay out there. Something's happening. 5 of these, that's -5, right? Now who thinks, what's the next step? What do I do?
Take away 2.
Yeah, this is beautiful. It's just takeaway. The minus in the middle just means subtraction, as it always does. I have 5 negatives, I want to take 2 of them away. So of course I get -3. Now, computationally, what would you do?
The 2 negatives make
The 2 negatives make a positive, which we still have to kind of establish. But there it is, it's -3. So when you do show this, you can go back to your manipulatives to show that's exactly what we would get the takeaway method, right? So this is sort of like, I always think about subtracting a negative as forgiving debt. If I owe somebody $5 and they forgive 2 of those bucks, don't I just owe them 3 now? So taking away negative is like forgiving debt. As a teacher, you desperately, I'm sure you start to see this, and hopefully I do this enough with you guys. You want to relate the mathematical concepts to something in real freaking life, right? Can you always do that? No, I don't think I can do that with every calculus 3 idea that I do, but a lot of it can be. All right, what about, what was the other one I wanted to do? Let me ask you this. So if I look at -5 plus 2, if I do that with these, what would be different? I would put 5 down, and then what would I do? Yeah, put 2 blues in. And of course that just leads to complete and total annihilation of 2 of these, and I still get -3, right? Okay, so I have 2 completely different physical approaches, and I get the exact same result. Okay, cool. So I want to do this other one. I'm kind of jumping all the way through my stuff, but it's good. We got this shit out, so we might as well do it all. Here it is. Yeah, okay. So let me make this really, really quick. What if I tried to do, let's do this one. It's not a brand new problem, but I'm just going to approach it a different way. -3 minus -2. So do that for me real quick. So this would just be, take 2 away, right? Okay, so that matches up with what we thought. All right, that wasn't the one I wanted to do, so this is the one I want to do. Oh, no. Come here, you go. I know you guys. So look at this one. All right, this one we're going to analyze the shit out of, so be ready. Where'd it go? There it is. 2 minus 4. 2, yeah, sure. 2 minus 4. Now here's the problem. I want it exactly the way it's said. So what do you lay down to start with? 2 blues. Can I take 4 away from that? Okay, so we're strictly living in the physical reality of the problem. It wants me to take 4 away from this. I cannot do that. What am I allowed to add to anything? And it won't change. 0. What's another way to say 0? -1 plus 1, right? Does everybody understand physically what the problem is here? And this, I don't know if you guys remember that video I showed you a long time, where it said 2 apples minus 3 apples is the anti-apple or something. It's all freaky because physically it doesn't make sense. I've got 2 things and I want to take 4 of them away. This is why civilization had the biggest problem with negative numbers, because it doesn't make physical sense. I can add 0 to anything I want. So can everybody grab 0 for me? Can anybody grab 0 for me? Hold them up. There we go, okay. So we all have 0 in our hands. That's awesome. What do you have in your hand? Nothing. So plop that down. Do I have enough yet? Can I take 4 away yet? No, so I'm going to do it again. Right, grab 0, throw it in there. Now can I take 4 away? Yes. So if I take 4 away, what do I get? Yeah? -2. Kick ass. Let me stop for a minute. You guys follow what just happened. Again, what's weird for you, and I understand this, is that you already, hopefully, understand negative numbers. This isn't supposed to be a big aha moment for you, but it's kind of neat to realize for somebody who has no idea about any of this stuff. They want to live with these. They want to live with these. They want this to be everything. So you start to pull them in the right direction, but living within these. I got two things, can I take 4 away? No. And then by this point, you will have told them this is nothing, this means 0. So putting these down does nothing to the problem. And all of a sudden, it'll take 4 away. That's a huge step. Okay. So here, you guys do this. Same way. What do you got, Jeff? 3 minus 6. Do 3 minus 6 the same way. That's not the best example, Jeff. It's too bad. It's too bad. I don't know if you have enough chips. Do you have enough chips? Okay, so 3 minus 6. So I gotta put 1, 2, 3, and then I can take that away, right? Got it. Okay, again. See the look on some of your faces. Not ground shaking, but I'm almost certain none of you ever looked at 3 minus 6 the way we just did it, right? Okay. So, let me do this. Bear with me. I want to kind of make a step here. I'm going to do it with smaller numbers. Let's do 1 minus 4. Okay. So let me do this one a little different this time. So if I put 1, what I'm going to do is something that seems a little counterintuitive. I'm going to add 4 blue and 4 red. And then I can take 4 away, right? Now listen. You guys agree with me? This is like overkill. You guys would agree with me? I like the look on some of your faces. It's perfect. You look like this. This is more than I need. Go with me. These come right away, immediately, correct? Any problem I had, whatever the shit number that is, if I add that many, I'm gonna immediately take that many away, correct? So this step is unnecessary, what I just did. And then what happens with what's left? Those two cancel. So what does this mean? So when I'm telling a student this, they understand that I can add as many of these as I want. If I add 4, that is silly because I would just automatically take those away. So what this shows is, what is 1 minus 4 equivalent to? It's equivalent to 1, and I know we already did this, but I haven't shown you concretely. What did I just do? That's equivalent to 1 plus negative 4. Yeah, I like it. And again, the idea that minus somehow becomes addition is exceptionally weird, right? In fact, I don't know if I've said this to you guys. Have I said this to you guys yet? There is no division. There is no subtraction. There's only adding the opposite. There's only multiplying by the inverse, right? This is basically what that is all about. Okay. The idea of subtraction is just a shortcut to the actual idea that there is no subtraction. Okay. Is there anything else I want to do while I got this? I'm kind of like way ahead of my notes. Well, sure. Let's do one more thing. How do you think I would do 3 times negative 4? This might be too many. Let's do 3 times negative 2. I don't want to. I'll make sure everybody's got the right number of chips. 3 times negative 2. What the shit does that mean? Remind me, what does 3 times 5 mean officially? 3 groups of 5. So what does 3 times negative 2 mean? Can you lay that out?
3 groups, negative 2.
Good. 3 groups of negative 2. And of course, you guys knew where I was going. What do you get? Negative 6. Now, here's where things get weird. What if instead the problem was negative 3 times 2? Now, listen, on one level, you all know that's the same shit. On another level, you all know that the way we've defined multiplication, that is different. This is weird. This means 3 groups of negative 2. This means take away 3 groups of 2. Do you guys see that? This is kind of like, right now I have nothing here, correct? And then what did we do? We added, because that's positive, 3 groups of -2. What does this want me to do? I've got nothing right now. What does it want me to do? Take away 3 groups of 2. I got nothing. I got nothing. What am I going to do then? I ain't got nothing. How am I going to take away 3 groups of 2? Is everybody with me, by the way? Negative. One application, one interpretation is take away. This was positive 3. So this said add 3 groups of -2. So we did. We put 3 groups of 2 reds. This says take away 3 groups of 2. I got nothing. How do I give myself something to work with? What do I do? Can I take anything away from what I've got? I've got nothing. We've done this just a minute ago. How do I give myself something to work with when I've got nothing? Add zeros. How many zeros am I going to add? Do I have 3 groups of 2 yet? Huh? No? Okay. So now I got 2 groups of 2. Are you agreeing with me? That's 2 groups of 2. So one more set like this, one more pair of stuff. Now I've got 3 groups of 2. Do you agree? 1, 2, 3. So I'm going to do what it says. I'm going to take them away. And what do I get? -6. Kick ass. Let me stop for a minute. I'm not sure what you guys are thinking, because on one level it's like, dude, the freaking answer is -6. Move the shit on. And that's what I hear from parents all the damn time that do not understand that this concept does not live in your head when you're born. This shit's got to be grown and built on, and right? You guys understand? So I know you guys know the answer was -6 either way. Little person, we made all this shit up. We made all this shit up. The symbols we use, the operations, what they look like, we made all that shit up. Little people born in the world, they got to catch up with all that shit. So we got to build these ideas. Okay. I like it. All right. Hang on to those. I might do some more with that, but we'll see. I'm not going to catch up with some details. Okay. See, where did we leave off? Let's see. See, good one. I like it. Oh, so let me kind of capture a couple of things real quick. When I taught Math 88, students have all these various ways of looking at it conceptually, and again, those are really good for people first learning negatives. When you get to a certain level, you need to let go of needing to think whole and climbing to do every single problem. You need to get past that. So when I tell people, tell me if you ever heard these 2 rules. There's 2 rules for combining signed numbers. If both signs are the same, you add them and put the sign back on, right? So obviously 5 plus 2 is 7. That's some shit right there. What's -5 plus -2? They're both the same sign, correct? So you add them, 5 plus 2 is 7, and you put the sign back on. So if both signs are the same, add and put the sign back on. If both signs are different, what do we do? So for example, 8 minus 11. Do you all agree with me? 8's positive, the 11's got a negative, right? So what do you do in that case? What is 8 minus 11? Negative 3. So couldn't we do 8 minus 11? 11 minus 8 is 3. But why is the answer negative? Because the bigger number was negative. That means I owe money. I owe more money than I got in that case, right? If you want to use money. So if both signs are different, subtract and put the sign of the bigger one. Right? And again, nothing ground shaking for us. All of you should be able to do 11 minus 15 or something. I'm just saying this is a really nice, if you happen to end up teaching a higher grade, instead of second or third, you're teaching 7th or something, then this is a nice rule to kind of capture all the stuff they've already learned. These are 2 immediate rules that work, independent of climbing out of a hole or whatever, or money. This is just directly computational. Okay. Yeah, good. So when we add integers into the whole mix, we inherit all the properties. So there's still commutative. When we're talking about addition, still commutative, it's still associative, still got distributive property with multiplication. We added the idea of additive inverse, right? So real quick, just to make sure you guys are with me, what is the additive inverse of negative 3/5? Additive inverse. Additive inverse of negative 3/5. Positive 3/5. That's it. That's all you did. Just change the sign, right? So additive inverse is the number I would add to make it 0. So it's just the opposite side, right? What is the multiplicative inverse of negative 3/5? Negative 5/3. Same numbers, just flip them. Okay, good. I like it. So obviously 2 very distinct things. Okay. Oh. All right, let me ask you this. Is negative A positive or negative? A really good question would be, what the shit's A, right? So I like that nobody said negative immediately. And some of you guys could pick up on the fact that this is not supposed to be something immediate. So you can't tell. You have no idea. It depends on if A is positive or negative, right? But I always get students, real quick little side note. Do you all know what these symbols are, right? So if I did this, what are those symbols? Absolute value signs. The answer for an absolute value always comes out positive, or 0 if it's absolute value 0. Does anyone know why, real quick? I don't think we talked about absolute value, and I don't think we do. But anybody remember why the absolute value comes out positive?
Distance away from 0.
Based on distance from 0. So that how far is 0 away from 0? 0. That's the one number that's not positive. Every other number, if I'm at 4, that's 4 away. If I'm at negative 4, that's still 4 away, right? Okay. So that's going to be 4. What's the absolute value of x? So what's the absolute value of 7? What's the absolute value of 7? 7, right? What's the absolute value of negative 7? 7. So when does the absolute value not do something? When it's already positive or 0. When does the absolute value actually do something? When it's negative. So when I ask you an absolute value question, what's the very first thing your brain does? It says, okay, is that number inside positive or is it negative? So what's the problem with that problem? The same thing we had before. We don't know what the shit x is, right? So you can't give me one answer for this. You would say, when would it leave it alone? When would the answer be x? When would the answer be x? What kind of number would have to be in there for the absolute value to leave it alone? Don't be specific. What would have to be true about the number? Sure, it could be 0, or it could be any positive number, right? When would it change signs? And how do I do that mathematically? What do I do to a number to make it change signs? Multiply it by negative. So it'll be negative x if x is less than 0. Okay. I'm not sure if any of you guys remember talking about that ever, whenever you did absolute value stuff before. In algebra, this would lead to 2 solutions for an absolute value equation because there's 2 situations that it could be in. We're not going to go there. Don't worry. Okay. In fact, that's a little more than I had to show you, but too bad. I did. Yeah, so I think I showed you guys this. If I look at a number line, and I consider 2 times negative 1. Now this is nothing, this is just an idea. This is not, I'm not going to step around, I'm not going to put 2 negative 1s. Remind me if I told you this. Multiplying by negative 1 is like rotating halfway. Have I said this to you guys yet? No, okay. Y'all, you said a lot of shit, Jeff. I don't know. Does it make sense, though? What's negative 3 times negative 1? Negative 3 times negative 1 is 3. And again, if you rotate halfway, there you are. You're at 3, right? So we're kind of sneaking up on why did 2 negatives multiply to be a positive? What would... So right here, we see it. Negative 3 times negative 1 goes back to 3. So if I do 2 times negative 1, that gets me here. If I then do negative 2 times negative 1, that would get me back. So there. So 1 negative just tells me to go halfway. 2 negatives would tell me to come right back. So it's kind of like turn. Now turn again. Okay, now I'm facing where I was before, right? So 2 negatives come out to be a positive because they effectively take me back to where I was. It's a full rotation. Okay, baby. Can somebody, how about this? Can you guys do this problem using your manipulators, using your blue and red chips? So remember earlier we did 3 times negative 2, that was relatively easy, and then we did negative 2 times 3, which is a little harder. How many groups do I want to make? 2 groups of, and do I want to add 2 groups or do I want to take away 2 groups? 2 is negative, so I want to take them away. And right now, I have a blank slate, right? I've got nothing. Oh, I might as well just draw it. Why not? I don't have to be up here. Awesome if I have red. No. Oh, too bad, Jeff. We'll use purple. Sure. Oh. I might as well do it. So if I have nothing and I want to do, what was it, negative 2 times negative 1? Yeah. Oh, there it is. It's right there. Neato. I would put 2 of these now. Can I take away 2 groups of negative 1 now? Yeah. So I take these, and sure enough, what am I left with? 2. Yes. So there's a manipulative approach to show that the product of two negatives comes out to be positive. I like it. What do I do with you? Oh, there you are. Let's see. Blah, blah, blah. Oh. So let's talk about subtraction. We already did a couple of subtraction problems, so just to officially talk about it. This is something I see every now and again. It actually is a pretty powerful way to illustrate a few different things. 6 minus 4, incredibly enough, is 2. 6 minus 5, that's crazy. So what seems to be happening every time I make this go up by 1, what's happening to the answer? Goes down by 1. So if I just keep doing that, make this go up by 1, if this goes down by 1, what do I get? -1. That's a decent kind of way to show somebody what 6 minus 7 is, how it kind of comes from just a pattern that we see. I like it. Okay. Now, we already proved something very powerful, which was if I have 7 minus -3, what does that become? 7 plus 3. I like it. Right, so 2 negatives make a positive. If I have multiple sign operations in the middle, I can condense them to be one operation. I like it. Let's see, what else? Oh, we did all that already. That kicks ass. Yeah. What about, do you guys remember missing addend? How did missing addend work? So if I wanted to know what 6 minus 2 was, how would I rewrite that to think about it from a missing addend approach? Yes, so I'd say, if this is something, 6 has to be 2 plus that thing. And then I can just think about it from in terms of addition, right? I don't have to memorize subtraction, I can just think in terms of addition. What did I add to 2 to get 6? And incredibly enough, I'll get out there. I get n is 4. So if I do that same thing to this problem, take a minute, try to do the exact same thing to that problem. Try to rewrite it the same way. All right, so what we got going on? So if 7 minus -3 is equal to something, that means that 7 is equal to -3 plus m. I like it. And of course, what do I take 3 away from to make it 7? 10. So that's another way to get at the answer being 10, based on this missing addend. So all the properties, all the different approaches for subtraction we saw before, missing addend being one of them, still works when you throw negatives into the mix. Okay, I like it. Okay. Let me ask you this. Yeah, okay. Make sure I didn't miss anybody. No, okay, I like it. What is this? Can somebody tell me what this is? relatively quickly. It's gonna be more than that. What's the only operation in the whole thing? Multiplication, right? 2 times 3 times 2 is in there, correct? So can't I break this up into 2 kind of parts? What's the sign gonna be? How can you quickly tell? Every pair of negatives does what? Kills each other. So what you're looking for is there an odd guy out? Because 2 will kill each other. Let me not flick you guys off. 2 will kill each other. So if there's an odd guy out, it's still going to be negative. How many negatives are there? 4. So they have 2 pairs. All the negatives died. So when you have a problem like that, you just look at the negatives first. What's the sign going to be? And then you just have to worry about 2 times 3 times 2, right? Which incredibly enough is. Okay. So this is the same idea as what is negative 1 to the 111th power? All right, let's start here. What's negative 1 squared? Negative 1 times negative 1.
1.
Good. What's negative 1 cubed? Negative 1 times negative 1 times negative 1. So it's always going to be some kind of 1. So the real question is the answer negative or positive 1? How many? Yeah, it's going to be negative. Why? Because you got an odd number of negatives. So 110 will form 55 pairs, and they fight. And you got the one dude over here going, I ain't getting in that shit. So he's alive at the end, that one little dude. Okay. Bam. Yeah, there's a, okay, yeah, let me do a couple things in a row here. All right, this is gonna seem silly, but it's all right. What is a times 0? 0. Cool. Doesn't matter what a is, right? A times 0 is 0. Isn't 0 1 plus negative 1? Right? Okay. And then couldn't I distribute this through? And then wouldn't this be a plus negative a? Incredibly enough, right? So actually, I could do a couple things. So number one, this shows that these are additive inverses of each other. If I go from this step, this is equal to 0. Subtract a from both sides. I'll get a times negative 1 equals negative a. Silly little side note. So that's just another way to show that multiplying by negative makes something negative. Astounding. I could do something similar with, is it going to be immediately obvious to somebody that a negative number times a positive number is going to be negative? Not necessarily. So this is equal to negative 1 times a times b, which is equal to negative 1 times ab, which is the opposite of this. So this is negative ab. All right, again, silly little things, right? And then finally, if I have 2 negatives multiplying each other, this will be negative 1 times a, negative 1 times b. This will be negative 1. By the way, what property am I using right now? Poor little b dude. What property did I use from here to here? From here to here, what property did I use? Yeah, commutative property, right? I just commuted these dudes, turned them around, right? So when individual things move, that's commutative property. Individuals commute. I know this is all like ground shaking. So negative times negative is positive, and I get AB, so the two negatives cancel. Okay. Crazy sauce. Then you get this thing. This shows up in algebra all the time, and I'm curious. I'm going to show you, you know me, I'm going to show you an example. If I know that A and B are integers, and they multiply to be 0, what's got to be true? One of them's got to be 0, right? Do you guys remember? I'm going to torture you as much as I can today. Do you guys remember from algebra using this property? This is officially called the zero divisors property. So watch this. Let me see if I can get you guys to really. Do you guys remember something like that from algebra? And you had to factor it. Does this look at all familiar? I don't know if you guys remember what this was called. So like x squared, x times x is x squared, correct? 1 times 1 is 1. And if I make the middle terms different signs, they cancel. Good old difference of squares. So don't I have, what is x minus 1? It's a number I don't know. What's x plus 1? It's another frickin' number I don't know. Don't I have two numbers multiplied by 0? Therefore, one of them has to be 0. So that's why the next step you would do would be this. And then you get x is 1 or x is negative. So we're just using that simple idea. If I multiply two integers together, one of them's got to be, and actually it's all two real numbers, and I get 0, one of them's got to be 0. Both of them might be 0. I don't know. But at least one of them has got to be 0. Blah, 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 blah. Oh. All right. Yeah, let's do that. So real quick, which one of these is bigger? -9. Okay, why? Be careful. All right, real careful. They're both negative, so what you just said is true. The way you said it sounds like that's how you tell period, right? Isn't 2 closer to 0 than 7, but 7's bigger than 2? Since they're both negative, that statement's true. So what would hold forever? What would just tell me something's bigger no matter what, if it's negative or positive? Why is -9 bigger than -11? Scale is awesome.
You can add something to 11.
Okay, cool. All right, beautiful. I wasn't even thinking going that way. What I was thinking was it's to the right of it, right? So any number to the right of another number is bigger. But no, Morgan, you like one step ahead of me. The next step would be, so remember what's got to be true if this holds. If something is bigger, that means that I have to be able to add something to this to make it become this. I have to be able to add a positive number to it. So -11 plus something must be -9. And of course, what is that positive number? 2. I like it. Kick ass. So I don't know if you guys remember, I think it was a test question. I said, find the number that illustrates the inequality. You had to find just the number that you had to add to make it. That explains why this one's bigger, because I have to add something to this dude to make it the same as that guy. So of course he's bigger. Okay, I like it. But you can see why students would get really confused about this. 11's bigger. Are you kidding me? Right? But no, officially, that's bigger. Okay. Does anyone remember if you had to solve this equation? Let me make it like this. So much algebra today. Oh boy. And remember, if you had to solve that inequality, what would you do next?
Turn the inequality sign into a equal sign.
No. Oh man, I'm sorry. Whoever your teacher was, I want to find them and have words. Because it sounds like that's the process you were explained.
Well, like, so pretty much what I would have done first was take -2.
Okay, good. And to do that, you would divide by -2. If I put this, I'm wrong. That is wrong. Does anyone know why that's wrong? What was I supposed to do?
Flip it with the sign.
Yeah, does anyone know why?
Because when you multiply by a negative number, or divide.
How did I define the multiplication by a negative number earlier? Wasn't it rotating around 0? Wasn't it rotating back? So when I multiply by a negative, I change what side of 0 things are on. I change their order. It's called a non-order preserving operation. Why does it not, if I had this and I divide by -2, all right, I'm stupid, but yeah, you flip the equal sign, it just looks the same. So real quick, just to illustrate why that's true. Why the shit do you flip this damn thing? I'll show you 2 ways. Which one of these is bigger? 1. Okay. What happens when I divide by a -1 both sides? What's this become? What's this become? Which one's bigger? 2 is bigger. All right. Why do you flip the sign? Because. I love that answer. Because that's how freaking numbers work, right? Another way to answer why I do it here, real quick, go with me, I'm sorry. So much algebra today. Instead of dividing by -2 right away, watch what I'm gonna do some weird shit. You ready? I'm gonna add 2x, and I'm gonna subtract 8. I don't think any of us would do that, right? But I could if I wanted to. So I did. So now I divide by 2, correct? Can somebody read that for me? -4 is greater than x, so therefore x is less than -4, which now matches. If I did not flip, that wouldn't match. That would not be good, because math has got to be coherent. It's got to be consistent, or else we throw the entire thing out. Not really. But still, we might. So I don't know if that makes sense. So it's a shortcut. Flipping the inequality symbol is a shortcut. Instead of making it positive by adding it to the other side, you keep it there, but you flip the sign, because it would have flipped to the other side of the damn sign. Does that make any sense? Okay. And again, it's a little further than we actually had to go. You're not going to go from chips meaning positive negative to algebra suddenly in the same day, but okay, only with me. I like it. Let's end right there. Let's have a really nice early day. Is that all right? So we'll finish up chapter 8 Tuesday. If somebody emails me and reminds me, I'll put the practice final up in Canvas early, so you can kind of get a start on it. Otherwise, I'll have hard copies on Tuesday. Okay. Yeah, this was 8.1 and 8.2. Yeah, I kind of sliced all the way through there. Oh yeah, thanks guys. Bring back my shit. Chips. Yum. All right. Where'd I put it? Here it is. Sure. There's more information on that grade sheet than normal. Okay, cool. Okay, I should have deleted that. I just haven't caught up with some of the homework stuff.
What is this variable?
Oh, good. All right, this is the new stuff. You want these to be low, because this is what you need to average. So on, okay, that's when I thought I was gonna have a quiz, but now the only thing left is the final.